Okay, just to finish up the rest of this screen recording for paper one, I promised Olive that I would take her to Target to spend some of her birthday money, so that was what I did this evening. But I also told you guys that I would get this in for you, so here we go. I'm leaving off on page 8, number 3. We've done this one before. Beginning of this year, seawater contains many different elements and compounds. So you're looking at sodium ions and chloride. Notice the ending ions and part of the sodium chloride crystal. So remember, it does make a crystal lattice. Solid ionic compounds do this. And then just some difference here. You have covalent bonds. I'm going to spell it right this time. Ooh. Here we go. And then you have ionic. Jeez Louise. So like two, coexist, co-inhabit, cohabit, meaning together or sharing. So covalent bonds share electrons, they share it equally. Where, like, we remember water is a polar covalent. They share, but they don't share equally. Okay, and so ionic is give and take, and it's just with electrons. You never trade around protons. And specifically from this question, you might remember that there were some like specifics in the terminology. When you're talking about them as their individual, their atoms, just straight from the periodic table. And then after that, whenever they start giving and taking electrons, they are going to be ions. So they start as atoms and become ions, but A in the alphabet comes before I in the alphabet, if that helps at all. All right, so these are all sodium, 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 and then chlorides. All right, so it's explained, this is why or how, this ionic structure forms from sodium atoms and chlorine atoms. So this is like what they are in their original form. And once they bond with each other, or they start giving and taking electrons, then those are what we refer to as ions. All right. First thing here, if we want to look at the periodic table or consider it, group 1 has one valence electron, and again, those are electrons that are in the outer shell. Group 2 has two valence electrons in its outer shell. We don't really consider the transition metals 3, 4, 5, 6, 7, and 8. And then I also taught you back in August, September about the octet rule. Octet meaning 8. So these atoms are going to want to have 8 electrons in their outer shell in order to be stable, so that they don't react with other elements again, or other atoms again. So sodium's right here in group 1, so we know it's going to have 1 electron in its outer shell. Chlorine's right here, and it has 7. In order for chlorine to be a heavy chlorine, it would like 1 more. For sodium, or it can lose 7. And for sodium, it would either need to gain 7 or just lose the 1. It's going to be much easier for it to lose the 1. And so chlorine needs 1. Sodium wants to get rid of 1. So they're going to bond really well together. All your group 1s and your group 7s bond really well together. Because group 1 is going to be giving their electron to group 7, meaning now the next orbital for this group 1 here, their shell will be essentially full, or their electron shell will be full, their orbital, And so will those in group 7. They'll be able to have that one extra that they need. Oops. So sodium will look like this. Chlorine. And then it has space for one more. It's going to get it from that one right there. And so now in sodium, sodium atom, chlorine atom. I'm not going to call it chloride until it has received that electron. Sodium is going to donate or lose or give one of its electrons away. And so now it'll look like this. It gave away one negative thing, where electrons are negative. So if it gave away one of its negativity, then it's going to become just plus one, just one more positive. All right, and then chlorine is going to accept that negativity. And so chlorine now is going to be like -1, it just has one more negative on it. And it's plus on sodium. It's nothing with the protons. You cannot exchange protons in the nucleus. That doesn't happen. It's electrons. Sodium is going, because it gave away something negative, now it just can become that much more positive. Chlorine took the negativity, just one of them, so now it's just going to be -1. And that's going to be our first marks. All right. A chlorine atom, whenever you're talking about it straight off the periodic table or as itself, it's an atom. Gains an electron. Sodium atom loses an electron. And here's your why. You're also essentially answering the how right here, those two. But the why, to fill the outer shell, which essentially makes them unreactive, or you can call it orbital. Or you could say like to fulfill or satisfy the octet rule. Okay, and then so why were they gonna, we just gave just like a short intro to this, but then why is this structure even forming though? Sure, they're giving and taking electrons, but then, again, you want to say why, like why do they do this well together? Well, it's all in this opposites attract here. You got the positive and you got the negative, and that's how we're going to finish out this answer. And you're also going to need to focus on some basic chemistry vocab. So notice now the chloride ion these are underlined in the mark scheme, the atom and then the ion has a negative charge. Or you can do the reverse argument. You can say the sodium ion has a positive charge. Okay, but then why do they bond to each other? Opposite charges attract. And this is where like they'll form that lattice structure. So another way to look at these is like, this is a negative, this is a negative, this is a negative, 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 right? So we look at that one right there. Negative, 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 negative. These are positive, 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 positive. And so that's essentially it. That's it right there. Draw one molecule of water to show the electron sharing that is present between the atoms. This is the only question I've ever seen Marine Cambridge have. Right, water is H2O. Here's your hydrogen. Because I shouldn't do the same color. Here's your hydrogen at the top. And then you got you got one oxygen, it's H2O, two hydrogens. So again, same thing goes. Hydrogen is in group 1, so they have a 1 valence electron in the outer shell, but we do have 2 of them. Oxygen is in group 6. Oxygen will need 2 more to be stable. And it's going to be able to get it from one of the hydrogens, electrons, and then the other hydrogen, because there's 2 of them, its electron. All right. And then I did teach this in like September, August, September. But hydrogen is unique. Hydrogen and helium are the only 2 in their row. Rows go across, groups go up and down. So 1, 2. There can only, in this first row, ever be a max of 2 electrons in that outer shell. Their outer shell, that first shell, can only hold 2 electrons max. Where, like this group right here, 1, 2, I'll do the laser pointer. So 1, 2, 3, 4, 5, 6, 7, 8. And this is going to be one that has that octet rule. Same with this one here. And then your transition metals always do some funky things, and I don't remember them, truthfully. Okay, so hydrogen is going to be like, yeah, I could give you an electron, but then I won't have any. Actually, I would like to have one myself. I'll let you borrow one of mine if you can let me borrow one of yours. The other hydrogen is going to say the same thing. Oxygen's like, cool, bet. I actually would like to have 2 more electrons, and each hydrogen is willing to share one. So oxygen will share its existing electrons, which it has 6 of them, with the hydrogens. All right. So there's the sharing right there and right there. So now if we count it, oxygen is going to have 1, 2, 3, 4, 5, 6, 7, 8. Oxygen is happy. And then the hydrogen had its existing one, which is the blue ones. And then they're sharing it, which is why it's polar covalent, with the oxygen sharing one with the hydrogens. And this is where we got that partial negative charge. Clearly, you can see that oxygen has more electrons surrounding it, has 6, where at any time hydrogen is going to have 2. So there is more negative things, more electrons surrounding the oxygen atom. And so up here we have a partial positive charge, and then down here, at the top we have partial negative charge from the electrons, and then at the bottom we have partial positives. Okay, a question you've had a bunch of times. Okay, where water is polar, there you go, describe how NaCl will dissolve in water. So essentially, like, how come this molecule, consider the positives and then the negative side, your positive side and your negative side, how come that can break this down? Well, this also has positives. Oops. It also has positives and it has the negatives. And that's how they're going to bond. Okay, so water is polar. Or you can reference, mention that it has a partial positive and partial negative charges. Oh, excuse me, and you can do a reverse argument. You can do a reverse argument with the next mark. So you can say, like, the sodium, which is positive, is attracted to the negative oxygen. Vice versa, you can say the negative chloride ion is attracted to the positive hydrogen on the water molecule. It doesn't matter. It's attracted, and that's positive. To the partial negative, it's not oxygen gas. Or you can say the negative chloride ion is attracted to the positive hydrogen atom. This breaks down All right, there goes the water one. Also, I figured out my mistake. 31. I'm sure this was like killing you guys. Like, what are you getting, parrot? Can't count. 31 and 14. 45. That's why I wasn't getting the right total. Productivity. Oh, sorry, I went the wrong one. All right, so in this one, you got depth measured in meters, and then salinity measured in parts per thousand. That looks like that. Salinity is the amount of dissolved solids in water. State, which is like, what do you see and why? The relationship between depth and salinity in the estuary. So this is your X, this is your Y. You're always going to say as the X increases, decreases, or stays the same, whichever it's doing, the title of the y increases, decreases, or stays the same. Because those are really your only options for how numbers change. They don't change, or they go up, or they go down. So depth 2, 4, 6, 8, 10, 12. This is continually increasing. And then salinity 20.9, 22.2, 23, 27, 29, and 30 is also continually increasing. We need to say why. This is just like your sentence skeleton. This first mark, it's not even a mark. It's just a way for you to write that anytime you see suggest or state the relationship. Excuse me. Okay, well, salt has mass, has density, it's going to sink. A fish could swim through this water column in an estuary. Explain how changes in abiotic features from increasing the depth from getting deeper could affect the availability of oxygen for the fish. So we want to know is like as it gets deeper. First of all, we'll mention if oxygen is going to increase or decrease or stay the same. Oh my gosh, I'm not going to make it to midnight. And what abiotic feature? Like what abiotic feature is going to control this? And then what is it doing, that abiotic feature, what is it doing to oxygen? So from chapter 1, and there's 3 ways we could look at this. I'll split it up. Chapter 1, we did talk a lot about the chemistry of the ocean and like physical processes, density, salinity, low density, halocline, pycnocline, thermocline. Okay, so we can say as salinity increases, so this is your abiotic factor, with depth, then we'll say the dissolved oxygen decreases. And you can put dissolved oxygen DO with a little 2. And this is just because the more salt there is, the less space there is for gases. Okay, temperature. Your temperature changes with depth. Okay. The dissolved oxygen is lower. I wish I could erase what I just said. I'm so tired. The dissolved oxygen is higher because the temperature is colder. We like our drinks to be cold because they hold gases really well in it. And then the other thing we could talk about pressure. Listed out on the mark scheme. But it could work. So pressure increases with depth. do I say that better? The high pressure, not dissolves. Is that even the word dissolves? The high pressure, I'll say increases gas, but specifically for this question, oxygen, solubility. And the last one you can have that's an abiotic feature is depth increases, so it's getting deeper. Light penetration decreases. And then we have less oxygen in the water because there's not as much photosynthesis happening. Oh my gosh, I'm so tired. Okay. I'm gonna finish this in the morning because I'm just a poor soul right now. But I'll do productivity, just to maintain it. Primary production is photosynthesis, but when you add in that ivity, it's rate, which is a speed. I keep saying you would get marks for this. It doesn't have to be identical to exactly what's on the mark scheme, but it would be the rate of organic material production. How fast photosynthesis is happening, how fast biomass is synthesized. Things that can increase productivity are greater light penetration, having nutrients, warmer temperatures, having carbon dioxide, which is never an issue, and having enough water in the ocean is also never an issue. All right, so definition. The rate rate of biomass or organic material production. And then the unit. So biomass, we measure mass in kilograms. And then rate is going to be like a speed, so like distance over time or an amount over time. So this could be like a meter squared over a year. That's typically what it is. Biomass, mass as kilograms, and it's in an area and it's in a year, because then that'll take into account the different seasons. Okay, let me stop there.